All right, third time's the charm. This is chapter 11, the solutions chapter. This is section 4, vapor pressure. This is actually going to be video 3 and 4. I'm going to break this video into 2 parts. Just a tad too long for one video, so 2 videos. So here's part 1, video number 3. All right, vapor pressure, definition of. Vapor pressure is the pressure of the vapor, the gas phase, over a liquid at equilibrium. This is a closed system. In a closed system, liquid particles of a pure solvent will escape from the liquid phase to the gaseous phase. Problem is, in a closed system, those gas particles cannot escape to the atmosphere. So what ends up happening is they kind of bounce around until they end up touching the liquid again and condensing into the liquid phase. So you get this cycle going. Top particles right at the edge of the liquid phase here. Liquid particles escape, bounce around a little bit, fall right back into the liquid phase. Liquid particles escape, bounce around a little bit, fall right back in. So you get a cycle going from liquid to gas, gas to liquid to gas, gas to liquid. Volatile solvents will have a higher vapor pressure, sometimes they just call it P for pressure, than non-volatile solvents. What does that mean? That means that if you have a puddle of water and a puddle of alcohol, the puddle of alcohol will be gone first because it is a volatile solvent. It's a volatile liquid, and it goes from the liquid phase to the gaseous phase faster than liquid water. Right. Volatile versus non-volatile. A non-volatile solute will have no tendency to escape from solution into the vapor phase. These are going to be your solids. A volatile solute will escape from the solution into the vapor phase. These are going to be your liquids. Non-volatile are technically solids. That includes molecular solids and ionic solids, but ionic solids will have a larger reaction with the solvent than molecular. All solutes will alter the vapor pressure of a pure solvent. Non-volatile solutes are solids. Will inhibit the escape of solvent particles, so they decrease the vapor pressure of the solution by reason of pure diluting it up. Ionic compounds will decrease the vapor pressure more than molecular compounds because ionic compounds will actually have a small interaction with itself and the solvent. And of course, if it's a polar, which ionic compounds typically are, if it's a polar ionic compound or a polar molecular compound, then it's going to react with the solvent, especially if the solvent is polar water, and you might get a larger decrease. It might inhibit the solvent even more than what we thought. So technically speaking, solids are not volatile solutes. Solids will not evaporate themselves, but depending on the solute, you might have a larger interaction with the solvent than you originally anticipated. Volatile solutes are volatile liquids. Volatile liquids will contribute to the vapor pressure of the solution because the solute that is a volatile liquid will also evaporate. Therefore, you have both the solute and the solvent evaporating, changing from liquid to gas phase. Now you've got them both contributing. Non-volatile, let's tackle that first. Traditionally, your solids, your ionic compounds, your molecular compounds. A non-volatile solute in solution. These solids will not evaporate themselves. They will only inhibit the evaporation of the solvent. Because of the two in the solution, solute, solvent, a non-volatile solute will not evaporate. The solvent still will. It's just the solvent will not evaporate as much as it did when it was just a pure solvent. And again, look at the pictures. In the pure solvent, this entire line, this very top row of liquid particles can escape. In solution, Your very top row is part solute, part solvent. You do not have as many solvent particles escaping into the gas phase in the solution because there are not as many of them right at that top row. So again, the yellow balls, those are your non-volatile solute. They're inhibiting, they're preventing as many solvent particles escaping into the gas phase. They are in the way. All right, Raoult's law. The presence of a non-volatile solute will lower the vapor pressure of a solvent by pure dilution reasons. So your pressure of your solution will always be less than the pressure of the pure solvent. The mathematical computation that accompanies Raoult's law, pressure of the solution, which is a mixture of the solute and the solvent, will be equal to the mole fraction of the solvent, which is the moles of the solvent over total, times the pure solvent's vapor pressure. And if you look at the mathematical computation, it's a logical relationship. If this goes down, so will pressure of the solution. 3 variables, the pressure units, doesn't matter. There are no units for mole fraction. Please don't leave it as a fraction. The vapor pressure of the solution is directly proportional to the mole fraction of the solvent present. As this mole fraction goes down, as the quantity of your solvent goes down, your vapor pressure above the solution will go down. All right, take a look at this graph. Perfect visual aid. Notice the mole fraction of the solvent from 0 to 1.00, which is corresponding to 100%. If it is pure solvent, the mole fraction of the pure solvent is 100%. So whatever the pure solvent vapor pressure is, and as you add a solute, your mole fraction of your solvent will of course decrease. You're adding more solute, you're having less mole fraction of solvent, decreases. As the mole fraction of the solvent decreases, so does the vapor pressure over the entire solution. There's a direct relationship between the mole fraction of the solvent and the pressure of the solution, and an ideal solution will show a direct relationship between the two. An ideal solution will have, typically, a similar solute-solvent interaction. Remember, like dissolves like. The solute merely dilutes the solvent. The solute is not interacting with the solvent. It is not attractive to the solvent particles nor repulsing the solvent particles. So there's no interaction between the two. It is just a dilution issue. So here's a couple of examples we're going to do. Please write down the information. These are 2 different problems, and we'll tackle them one at a time. Okay, so here's what we did. I wrote down the information, first 3 lines. They give me sodium sulfate in water, ionic compound in our typical solvent of water. This is a solution. Solute is sodium sulfate, solvent is water. They give me the pure solvent's vapor pressure, 23.764 at 25 degrees Celsius. What you have to realize for ionic compounds is if it's a soluble salt, usually it's going to be, the number of moles is not as cut and dry as you originally thought. 0.246 moles of the compound, but there's technically no compound in the water. It's a soluble salt. So you only have the ions, sodium ions and sulfate ions. It's a 2-to-1 ratio for sodium to compound, 1-to-1 ratio for sulfate to compound. Therefore, instead of having 0.246 moles, you have 0.738 moles of ions total. So be careful of soluble salt. Plug it in, mole fraction of the solvent times the pure solvent's vapor pressure, and you will notice that my ionic compound in the water did indeed lower the vapor pressure of the solution. Not by a lot, but it still lowered it. By reason of dilution, by reason of inhibiting the solvent from escaping, the sodium sulfate lowered the vapor pressure of the water. All right, this one is a molecular compound, not an ionic. This is not a soluble salt, so it does not inhibit the solvent particles from escaping as much as the ionic salt did. This is sugar. So yes, it still lowered the vapor pressure of the solution, but not as much as the ionic salt. All right, this is the end of part 1. Part 2 is the next video.